Hello, my name is Nathan Boyd, and I am here to present our work on task and motion planning for bipedal locomotion and push recovery. Locomotion planning produces dynamic behaviors but often lacks decision-making abilities. Task planning is a powerful technique for decision-making and planning, but it only considers discrete instances and is thus not flexible to disturbances or errors. Legged robots commonly fall due to poorly timed disturbances and aggressive turning, where collision constraints can arise. One way to remedy this is with the cross-leg motion, which humans use under constrained gait circumstances. Most locomotion planners also don't consider high-level task planning logic at the locomotion level, making complex motions difficult to interpret. Typical locomotion pipelines directly handle disturbances with motion planning and control. However, our pipeline incorporates real-time task planning using linear temporal logic-based reactive synthesis. We use the dynamics at keyframe points in the center of mass phase space to dictate state transitions. A robust behavior tree middle layer then handles any discrepancies between the discrete task and the continuous motion planning level. The task planning layer operates as follows. First, we construct a two-player game between the environment and the robot with reactive synthesis offline. Imagine this like a game of chess, where the queen must move its position based on its dynamics. The decision maker then provides desired key point transition actions based on the current keyframe to the behavior tree and the motion planner. The LTL will plan for multiple steps by composing together single steps. Here we show simple forward walking with a stable limit cycle. For lateral disturbances, the LTL produces a single step that can return the lateral velocity to 0 while walking forward. Multi-step cross-leg motions do not always terminate with 0 lateral velocity, but do transition footholds. This allows the system to follow up with the previously mentioned single-step disturbance rejection technique. To safely execute these transitory actions with more detailed constraints, we formulate a whole-body optimization problem with kinematic, contact, and self-collision constraints. Here we show stable recovery motions from multiple disturbances while walking. The LTL composes a multi-step plan using the full-body actions. Perturbations from the left, back, and front can recover in one step, while perturbations from the right force a cross-leg maneuver that transitions to a one-step recovery to return to stable walking. This is further quantified by examining the instantaneous velocity impulse for one walking step at various phases and angles for a single stance foothold. The left half plane of this graph represents a single step disturbance rejection, and the right half plane represents cross-leg disturbance rejections. Lastly, we show the tracking, control, and disturbance rejection capabilities of the proposed method in simulation to determine its effectiveness. Thank you for watching.